Welcome, ladies and gentlemen, to Pre-Calculus Foundational Skills Week 3, where myself, Brian McLogan, is getting you prepared for pre-calculus. So in this kind of live stream, what we're going to talk about is simplifying rational expressions, rationalizing the denominator, evaluating using the unit circle, how to find the missing angles of a right triangle using trig, and then also parallel lines and a transversal. And again, guys, this is not a in-depth, training on each of these topics. That would take a very, very long time. But what I am doing is I'm covering a couple questions in each of these sections to help you prepare for the workbook, the summer assignment that I have for you guys to download, because I feel like if you go through this training as well as do the problems that I have in that workbook, you are going to have a really solid foundation when the school year starts. And again, that is true for students that are taking pre-calculus, college algebra, algebra 2, or even, calculus. I'm not sure if I said calculus or college algebra, either way. But, obviously, I am teaching pre-calculus again this year, so that is the design of the course, but a lot of these math skills are fairly basic, that they can definitely help you out. So just want to go through another pre-calculus tip, number 3, that a lot of students think of pre-calculus sometimes they get confused and they're like, it's going to be difficult. And it is a difficult course. It can be very difficult, especially some of the topics that we cover. But I always like to remind students that, don't overthink it. Pre-calculus is really just a combination of algebra 2, trigonometry, and then some calculus topics, really some kind of foundational stuff. So the algebra 2, a lot of times we'd expand on what you've already learned, and sometimes students, forgot what they already learned, so that's why that becomes difficult. Trigonometry is obviously a new concept for many students. We covered a little bit in like geometry, but obviously we get a much more advanced into the trig. But really, when you just kind of break things down, you can really fairly basic concepts with the trigonometry that we just expand upon. And the same thing with the calculus topics. It's really just hitting little topics here and there that we further explore in calculus. So, if you come into problems or issues of understanding in pre-calculus, just try to slow down, try to really understand where it is that you're having trouble. A lot of times it comes into just prior knowledge, or thinking that the concept that you're trying to learn is really just more complicated than it is. So really try to, don't overthink it and try to slow things down and break it down. All right, so the goal really for this live stream is really to kind of build up that understanding of trigonometry, what it is you should know, as well as understanding angles and the angle relationships. And we're going to do that with parallel lines as well as with triangles. So I cover a couple more because there is some problems with rational expressions. So that's why we're going to kind of start with that first. So obviously this is a very heavy algebra 2 topic. Is the rational expressions, but it is something that we do in pre-calculus, and it's one of those topics that students really struggle with. So that's why I just want to kind of cover these two problems. We have already covered some factoring in my previous week 1 as well as in week 2 training. So if you are weak on factoring, I would highly recommend that you go back and check those trainings out. So whenever we're simplifying a rational expression, if it doesn't have any restrictions on that, then we just want to make sure we understand that we cannot divide by 0. So we always want to find the values that are going to make the denominator equal to 0, because those are going to be undefined values. Okay, those are what we call like our restricted values as well. So it kind of depends on the examples. In this case, we're just going to simplify it, but I will kind of remind you of what are the restricted values, meaning what are the values x cannot be. So first thing, whenever we see a rational expression, is think of factoring, right? And you can think of factoring in a couple terms. Whenever you have a binomial, you would always kind of think of either difference of 2 squares or factoring out the GCF. All right, those are, and you could also do difference of 2 cubes, but that's not something I highlight as much, at least of course we do cover it, but not a very big topic. Or at least it's not something as common as you will see as far as GCF and difference of 2 squares. So immediately in this numerator, I notice that I can factor out a 3 and a x squared. So that's exactly what I'm going to do first here. I'm just going to factor out a 3x squared. When doing that, I'm going to be left with a x. I don't think I wanted that. An x minus 1. All right, so therefore I have a 3x minus 1. I think I just wanted an x. Oh, you know what? All right, well, let's just do it this way. So then in the denominator, you can see that they all share a x squared as well. So if I factor out an x squared, that will be leaving me with a x squared minus a 2x plus 1. Okay? So now again, before we go ahead and simplify everything out, and everything go crazy, like let's see if we can further factor this down. We recognize this to be a trinomial, a perfect square trinomial. So I can further factor that down into 3x squared times x minus 1 all over x squared times x minus 1 quantity squared. Okay. Now, when we're really thinking of this quantity squared, that's really the same thing as x minus 1 times x minus 1. Okay. So this is important because here we can apply the division property. So what the division property tells us is whenever we have a number, a term, or an expression divided by itself, separated by multiplication, we can divide them to 1, right? X squared divided by x squared is just 1, right? We can say cancel out. It's not really a great mathematical term, but it's, a lot of things, that's something that sticks. But you can see we can cancel those out because the x squared is separated by its terms with multiplications. And the same thing goes for x minus 1. The x minus 1s, those divide out, right? Even though there's a minus, but that's inside of the expression. So we can still divide those out, and therefore we're just going to be left with the expression of 3 over x minus 1. Now, there's nothing further we can do here. That is going to be fully simplified. But we do want to go ahead and list the values that made our denominator equal to 0. And typically, this is best understood or viewed when we have our expression fully simplified, or at least fully factored out. And just kind of going back to there, you can see that, well, when x is equal to 0, then that makes my whole denominator equal to 0. So I don't want x to be 0, as well as when x is equal to 1, that's going to make my denominator equal to 0, right? Because if x was 1, that'd be 0, and 0 times anything is going to be 0. So I'm just going to add in these restrictions. X cannot equal 0, and x cannot equal positive 1. All right. So now getting into the next example. Now we see that we have something to the 4th power, but I can't factor this out, right? I can't factor out an x to the 4th. So this one kind of gets students pretty confused when we deal with this in polynomials. So what I'm going to do in this case is I'm just going to say, forget about the x to the 4th. What if this was just like a normal quadratic trinomial? Like what if it just looked like this? How could I factor that out? All right. So again, this is like a little sidebar. And if I wanted to factor that out, I could say, well, that's going to be x minus 2 times x minus 1, right? Because we kind of practiced our factoring in the last 2 trainings. So if you recognize this, we know a trinomial is going to be a product of 2 factors. So we know that this is going to be the 2 factors, x minus 2 times x minus 1. The problem comes in is x times x does not give you x to the 4th. It gives you x squared. So all I need to do is just raise the powers, right? Because x squared times x squared is x to the 4th. I still need negative 2 times negative 1 to give me positive 2. So it still works. And if you do the middle terms, they're going to add to give you a negative 3x squared. Now in my denominator, I have another binomial. But I recognize they have an x in common. So I'm going to factor out the x, and that's going to leave me with a x squared minus 1. And again, in this case, you can see that those are going to divide out. So that's just going to leave me with a x squared minus 2 divided by x. Now here's something that happens that's important. Is the x squared minus 1, that got divided out. But that doesn't mean those values are still, are now going to be defined, right? So whenever you're identifying the restricted values, you have to go back to the original equation. Because what I want to do is I want to say, what numbers are going to make the denominator equal to 0? Well, obviously, when x equals 0, the denominator is going to equal 0, right? So we say x cannot equal 0. Well, what else? Well, we have this expression. So if I can just say x squared minus 1 equals 0, you could go ahead and solve and say x equals plus or minus 1, right? And again, that works because if you plug in 1 as well as negative 1 into this equation, you're going to get 0. So I'll just say x cannot equal plus or minus 1. So even though it got divided out, just like it happened over here, make sure that you still understand that those are still going to be restricted values. And that was also something we talked about. Remember, those are holes. We talked about that in our discontinuities last lesson. All right, moving on to rationalizing the denominator. So this is one that's, kind of interesting because technically, we don't always have to rationalize the denominator. In some chapters and in some problems, we want to, and it's going to be very helpful. Obviously, we start to do this with different applications, such in like trigonometric identities. So this understanding of the rationalizing the denominator is very important. So we've done them previously, if you remember in Algebra 2, with complex numbers and everything like that. But really the idea is not so much, yes, you could think about it in terms of like simplifying, but really I just want you to understand what is this goal? What is happening when we rationalize the denominator? So real quick, I'm just going to go through, if we have an expression like x plus 2, if I multiply it by or I'm sorry, x plus 2, a plus b, and I multiply by a minus b. What that gives me is the difference of two squares, a squared minus b squared. Now, this is very important for a couple reasons. If I'm squaring these denominators, if I'm squaring the square root, what that's going to do is that's going to undo the square root. So if we want to have an expression where we do not have a square root in the denominator, that's why rationalizing the denominator is so helpful. In terms of complex numbers, like when we don't want I to be in the denominator, well, I squared, right, if you remember, is going to be -1. So when we rationalize the denominator with I, that gets rid of the I in the denominator. And the same thing with the trigonometric functions. We want our trigonometric functions to be squared. That opens up different identities for us. So the main thing that we were going to want to do when we want to rationalize the denominator is you got to be careful. We don't want to multiply by the square root of 6, because if you multiply by the square root of 6 on the top and the bottom, right, well, that gives you the square root of 6 minus 6. So it's still going to give you a radical in the denominator. So what I want to do in this case is multiply what we call the conjugate. So that is going to be 1 plus the square root of 6. Okay, now again, this produces the difference of two squares, so I'm going to put this in parentheses. But again, the difference of two squares, we don't need to multiply everything times everything. We can just take the first two terms squared. 1 times 1 is 1 squared. So let's just say on the numerator I have square root of 2 times 1 plus square root of 6. Okay, so 1 times 1 is 1. And then negative square root of 6 times negative square root of 6 is going to be a -6. All right, now we can distribute here. So square root of 2 times 1 is going to be a square root of 2. Square root of 2 times square root of 6. Remember, when we're multiplying radicals, we're going to multiply the radicands together. So that's 2 times 6, which is going to be 12. And this is going to be a -5. All right, now, again, we could further simplify the square root of 12, right? The square root of 12 can be broken down into 4 times 3, which is 2, radical 3. All right, and then there's just really kind of comes into many, many different ways of rewriting this. You could put the you could put the 1/5 in front. You could just rewrite this as square root of 2 plus 2 radical 3 over -5. So let's just write it like that. Another way, just real quick, I'm not going to do it for the other one, but you could also write it like this. I mean, it really kind of depends on how your teacher, professor, textbook, wants the answer. But yeah, so that's basically, you can see the nice thing about this is that we just don't have a rational expression with the radical in the denominator. So in this case, we're just going to do the exact same thing where we recognize the conjugate. So it's going to be 1 plus the square root of 6. So 1 plus the square root of 6. The only difference here is now I have a binomial in my numerator, which is not the conjugate. So I'm actually going to need to expand that out. I'm going to actually need to multiply everything times everything, do a little FOIL practice. So let's go ahead and do that in the numerator. So that would be, let's see, 1 plus the square root of 6 plus the square root of 2. And then that's going to be plus square root of 12. My denominator, this is exactly the same. So I'm just going to rewrite that as a -5. And then up here, it's just going to be combining like terms. Well, again, remember, we can only combine like terms if they have the same radicand. Well, I can simplify this, right, to 2 square root of 3. And so we have 1 plus the square root of 6 plus the square root of 2 plus 2 square root of 3 all over -5. And you might say that does not look any more simplified than that problem. And I would have to agree to you. But again, the idea is just to understand this rationalizing the denominator because we will be using it in a couple different applications throughout the course. All right, so the next one is the unit circle. Now, when I used to teach Algebra 2, we used to not cover trigonometry at all. And trigonometry has kind of, got itself, wedged itself into the Algebra 2 curriculum, which is a whole nother video on its own. But most students that I have encountered in precalculus have at least a basic understanding of the unit circle. I am not a big proponent of memorizing the unit circle by any means. We do a lot of practice on the unit circle in my class, and I explain the unit circle, and we spend a lot of time understanding the unit circle and being able to evaluate using the unit circle. So what I'm going to do for this video is I'm just going to assume that students have at least been presented to the unit circle and at least understand or at least know the first couple points in this first quadrant, okay? Because I think all the points that I picked, are relative to the first couple quadrants here. And I'm not going to go crazy with my explanations here because I spend so much more time in precalculus explaining and having students understand these points because I think it's really important that students understand where these points come from. So therefore, when they're using them, they can understand, you know, if their points and everything makes sense or not. Let's see, square root of 3. Oh, you're going to do it to me? Okay. All right. So, again, this is a, you know what? I don't need, let's put this right there. Let me move this right. I ran out of room. Let's go right there. Yeah, I don't need a lot of room. Okay. I'll put that right there. Perfect. And then let's put a 3 here. Okay, so again, this is just the first quadrant of the unit circle. And remember, the unit circle has a radius of 1. These are going to be 3 angles. That is 30 degrees, 45 degrees, and 60 degrees, also known as pi over 6, pi over 4, and pi over 3. So we're going to want to make sure we understand the difference between radians and degrees. And again, we spent a lot of time with that. I think actually either way, I think actually I might actually change this. I'm not sure. I don't remember if I covered radians with my students, but maybe I did in Algebra 2. I'm trying to think. But either way, I'll write the degree formula as well for each of those. So anyways, if I want to evaluate the sine of 30 degrees, most students come into precalculus maybe having memorized that the sine represents the y coordinate on the unit circle. And, you know, somewhat that is true. So if we go to 30 degrees, that's going to be the smaller of the 3 angles. And then the y coordinate is just going to be 1/2. Okay. So again, remember the sine is the comparison of the opposite side of a triangle over the hypotenuse, right? But we can also think about it as this y coordinate on a point on the unit circle. And again, I'll make that connection throughout the course, but I think it's just important for students to understand these two kind of areas here, because really, actually, let me just do a quick little thing. That is the height, and remember the hypotenuse is 1. So 1/2 over 1, you can see is 1/2. So opposite, right? That's the height, opposite over hypotenuse. All right, the next one is cosine of negative 45 degrees. So 45 degrees is right here. So cosine would be like 1/2, right? So negative 45 degrees is just going to be in the opposite direction. So that's going to be going down here. Well, if you think about this as just a reflection, if this is over square root of 2 over 2, well, this, you can see that this is going to be the exact same, right? If you go 45 degrees up or if you go 45 degrees down, the x coordinate is still going to be exactly the same. So that's going to be the square root of 2 over 2. The reason why the unit circle is so powerful is because we cannot use triangles to evaluate for the tangent of 90 degrees. That just doesn't make any sense to us when we're looking at a triangle. However, if we look at this coordinate point here at 90 degrees, that is going to be 0, 1, because again, remember the radius of this circle is 1. So tangent represents the opposite over the hypotenuse, right? If you were thinking about this opposite over hypotenuse, that would be the same thing as the y over the x. So in this case, if we have y over x for a tangent, you can see that that is undefined. Now, that's not always the case, because we could also look at the tangent of 0, and that would be 0 over 1, which would be 0. So just don't think that because tangent is on an axis that it's going to be undefined. Remember, it's just always y over x. But whenever you're dividing by 0, that is going to give you an undefined value. For the next one, d, that's going to be 2 pi over 3. So if we said, and again, 2 pi over 3 is the same thing as 120 degrees. So let's just kind of think about this in terms of degrees. I don't know why I wanted to introduce radians here. I just wanted to keep it simple. But either way, that's the way it started. So let's just kind of look at 60 degrees. So from here to here is 60 degrees, right? And therefore we know that another 60 degrees is going to take you to 120, right? So if you were to kind of like finish this circle, you can see that that is just a reflection. So the sine is, remember, representing the y coordinate. So if we have the sine here of sine of 2 pi over 3, that's going to be square root of 3 over 2. And again, as I reflect this over, right, here's 60 square root of 3 over 2. Over here, the only thing that's going to be negative is the x coordinate, right? Because as we go to the left of the y-axis, the x coordinate is negative, but the y coordinate is still positive. So therefore, this is just going to be a square root of 3 over 2. Then let's go ahead and take a look at, I could have done 150, that would have been. But let me just kind of real quick, what if I would have done cosine of 150 degrees? So here's 30 degrees, right? And if you were to kind of rotate this like 30 degrees off of the x-axis. So here's 30 degrees off the x-axis, 0, so that's 30 degrees. And if I did 30 degrees off the x-axis over here, like halfway around a circle is 180, so you can see that would be 150. The important thing I wanted you to see here is this is going to be a negative square root of 3 over 2, right? Because when you go to the second quadrant, you can see that the x coordinates are all negative. Anything down below here, like for instance, if I did the sine of negative pi over 4, that would be a negative square root of 2 over 2, right? Because look at this point down here. That's in the fourth quadrant, I'm sorry. So the sine, the y coordinate is negative. So I could have done a little bit more problems, I guess, to kind of further drive home the points. Cosine of 0 in this case, 0 degrees is right there. So their cosine represents the x coordinate, which is just 1. And again, it's very difficult to think about or to conceptualize what is cosine representing. You know, when it's 0 degrees, that's not going to make up a triangle. So by looking at the unit circle, we can see how that makes sense. And then not but last least, I don't know, I can't even talk anymore. That's going to be tangent of 60 degrees. These ones always get students because again, tangent is y over x, right? So if we have 60 degrees here, that's going to be the y coordinate, square root of 3 over 2, all over 1/2. So now we have a fraction divided by a fraction. Well, what we need to do is, again, multiply by the reciprocal, right? Because in the previous trainings, we practiced this multiplying fractions. That goes to 1, and therefore those divide out, and we're just left with the square root of 3. So even though it looked like a very confusing problem, we can simplify it very, very smoothly. So that is just a brief little overview of these main points that are on the unit circle, as well as what happens when we take these points or we take these angles out of the first quadrant and we start discussing them on the axes, as well as in the second, the fourth, and the third quadrant. And I didn't do a problem in the third quadrant, but just remember in the third quadrant, the x and the y values are both negative. All right, so now let's go and do some missing sides and angles, because once we start talking about the unit circle, students completely forget about the meaning of our trigonometric functions. Like they just remember sine is y, cosine's x, tangent's y over x, and they completely forgot that they're still triangles, right? And that's why I kind of made that mention up here, is like, this is a triangle. Like that's what the unit circle is made of. It's made of special right triangles. So the unit circle is just a tool for us to more easily evaluate our trigonometric functions. Now, I decided to not use angles that were not on the unit circle, because again, if you didn't have angles that were on the unit circle, you just use a calculator. So the main thing I want to do is just remind you that to use your trigonometric functions, you have to have right angles. And also what you need to do is you have to have right angles. And what else do you need? Oh, you need to set up an equation. Okay. So in this case, in previous training, we just kind of talked about using the Pythagorean theorem and just setting up the ratios. So hopefully now you have a little bit of an idea of or you remember what the ratios were. So now let's actually put them into action. Okay, so in this case, I have an angle and I have the opposite side and the hypotenuse, right? Because remember the hypotenuse is always directly across from the 90-degree angle, and the opposite side is always opposite of the angle, okay? So we have a opposite and we have the opposite side and the hypotenuse. So we need to think about which trigonometric function represents the opposite and the hypotenuse, and that is sine. So I can say the sine of 30 degrees equals the opposite side over the hypotenuse. So if I want to solve for x, all I need to do is get 4 off. I just need to solve for x. So I'm just going to multiply by 4 on both sides. I'm just going to rearrange this here. So x equals, the 4 times the sine of 30 degrees. Now, this is where kind of knowing your trig is helpful, right? Kind of going back up here, what is the sine of 30 degrees? Well, sine 30 degrees is right here. The sine is represented by 1/2. So now I can just say, oh, okay, so sine of 30 degrees, that's 4 times 1/2. You don't need to use a calculator, right? Well, at least here, because we have a point on the unit circle. If it wasn't on the unit circle, then you'd obviously need to use a calculator. But you can see how useful this is, especially for you to know these points on the unit circle. Like you can, sine of 30 degrees, that's 1/2, and then you can go and evaluate. That was supposed to be there. Sorry, I messed that one up. All right. For the next example, now we don't have the opposite side anymore. We still have the hypotenuse, but we have the side that's between the angle and the 90 degree. That is what we call our adjacent side. So in this case, I'm going to need to use cosine. So I say cosine of 45 degrees is equal to my adjacent over my hypotenuse. Now the problem here is we have our variable x is in the denominator. So I need to do a couple different steps. I need to multiply by x on both sides to get the x off the denominator. And then I need to divide by cosine of 45 degrees. Okay, so x equals 2 divided by the cosine of 45 degrees. All right, again, let's go and look at our unit circle. Cosine of 45 degrees was that middle angle. That's going to be square root of 2 over 2. So this is going to be 2 divided by square root of 2 over 2. Well, crap, I have a fraction in the denominator. I do not want a fraction in the denominator, right? So what I'm going to do in this case is I'm going to multiply by the reciprocal. Okay, that means those are going to divide out. That divides to 1. Those divide out to 1. That leaves me with 1 over the square root of 2, which now I can rationalize. I don't need to multiply by a conjugate because there's no addition or subtraction, but I can rationalize the denominator here by multiplying by the square root of 2 to get it off the denominator, which is square root of 2 over 2. There you go. All right. And the last example, where's my thing? Oh, there I had. My last example is going to be, what am I doing? What did I do from there? I didn't want to do that. Oh, okay. No, let's do, sorry, that needs to be, I'm messing all this stuff up. Uh-oh. Oh, I got this. Let's do that. No, that's not going to work. That's not what I was thinking of. Okay. Crap. I moved this around and now I'm trying to think, well, I guess I'll just do this one. Hold on. Let me check this out. Sorry, guys, for the delay. Something is not right. Okay. That's square root of 2 over 2 divided by x. I made a mistake here. That's multiplied by x on both sides, divide by that. So that's going to be square root of 2 over 2. Oh, I'm sorry. That's going to be 4. No wonder. I was wondering where my mistake was. So I said those divide out. Those don't divide out. That's in the numerator. I was wondering what happened here. So that is a 4 times square root of 2. Those divide out. That gives you a 2 square root of 2. There you go. I wonder something was wrong because remember the hypotenuse is always the larger side. So you got to think those do not divide out. That was a big mistake there. Okay. Just be careful because it looked like it was in the denominator. So my brain like went that way. But again, that's in the numerator. Like that is like really 2 over 1. So sorry about that. All right. In last example here, again, now we're going to have the same thing. We're going to be using cosine, but now we don't know what the angle is. So again, we're still going to set up our ratio. So cosine of x equals 3 over 6. Okay. Well, cosine of x equals 1/2. Now, in this case, what we want to do is be able to find the angle. So we want to say cosine of what angle equals 1/2. Now, without getting into our restrictions and everything like that, let's just kind of look at, we know that the angles in a triangle have to fall between 0 and 90 degrees, right? So by looking at our angle in our triangle, we say, all right, which of these angles matches when the x coordinate is 1/2? And you can see it's that angle right there, which is 60 degrees. So we can just say x equals 60 degrees. So again, you could also rewrite that in your calculator. X equals, if you remember, that's the inverse function. Cosine inverse of 1/2, which again would be 60 degrees or pi over 3 if we were kind of talking about radians and so on and so forth. So just a quick little review. Remember, when we're using our trigonometric functions, we're finding the sides of the angle, and we're going to use our inverse trigonometric functions when we want to find the actual angles of a triangle. All right, and then last real training that I wanted to cover with you guys was just understanding the parallel lines and the transversal. You don't need to remember you don't always have to have parallel lines and a transversal, but because again, there's a couple things you should remember. In this first example, we can see that these are what we call vertical angles. And remember, vertical angles are what we call congruent. So x is equal to 30 degrees. Right? So when you have two intersecting lines and you have angles on opposing sides of the intersection, then those two angles are going to be congruent. Here we have what we call a linear pair. We have two angles that are supplementary. They're going to add up to 180 degrees because you can see they have the shared side and they make up a line. So we can say x plus 80 degrees is equal to 180 degrees. They are supplementary. They add up to a line. So therefore, we can say x equals 100 degrees. Now, I didn't need parallel lines and a transversal. I was going to do more of the, what you need to know for parallel lines and transversal, but really, I think there's kind of two of them you know. These come up a lot. This comes up a lot. So it's kind of important for you to remember those. The other two that come up is alternate interior angles or alternate exterior angles. And we should note that you have to have parallel lines for you to have either of those properties or to use those theorems. So the alternate interior angle says that when you have parallel lines and a transversal, then that these two angles, these alternate interior angles, they're both interior of the parallel lines, but they alternate on sides of the transversal, are going to be congruent. So x is going to equal 75 degrees. That is also the same thing for alternating exterior angles. So that works as well. And then the last one is going to be also that our other angles that are congruent is what we call corresponding angles. So corresponding angles are angles that are on the same side of the transversal, right? And kind of like both above or both below your parallel lines. So you can see how they're kind of like in the same position here. And these are going to be equal as well. So that is something that just kind of comes up, especially when we do our applications of trigonometry unit. We kind of go back into trigonometry and a lot of students or geometry, I'm sorry. And a lot of students have forgot those angle relationships as well as the, triangles and the angles and the sides of a triangle. So that's why, it's fairly simple stuff, but it's some stuff that, I think it's very helpful for you to just kind of have a brief little refresher on. All right, so just a little review. What we covered from this training, guys, was we simplified rational expressions. We practiced rationalizing the denominator. We practiced evaluating the unit circle, finding the missing sides and angles of a triangle, and then as well as doing finding missing measures using parallel lines and a transversal.